Morning, ladies and gentlemen. Welcome to Calc Review 18. And there were a lot of you that asked about parts B and C of each of these questions. I didn't see too many questions about part A, but I will go back and check, and I might add them to this video. But here's the first question that you were given. You're given a rate of change in baby bird weight with respect to time. So this is basically how fast is that weight changing. So part B, I'm going to skip part A because again, I don't believe I saw questions about it. But basically the general idea behind part A is just plug in 40, plug in 70, which one leads to the higher number. That higher number would represent the faster weight gain, right? Because you're solving for dB/dt, rate of change in rate with respect to time. So on to part B. First, let's start out with finding the second derivative. All right, so this is what we're given originally. So dB/dt is equal to 1/5 times 100 minus b. I distributed that 1/5 and rewrote the expression as 20 minus b over 5. Okay. Now to differentiate, I need to apply ddt to both sides. All right, so I apply this operation. This is the derivative operation, and I'm applying it to both sides, just like you would with any equation. Whatever you do to one side, you do to the other to balance, to maintain balance. Okay, so on the left side, when I apply ddt, I simply get d squared b over dt squared. On the right side, when I differentiate 20 with respect to time, I get 0 because that's a constant. When I differentiate negative b over 5 with respect to time, I get negative 1/5 dB/dt. What we have to understand here, remember, b is itself a function of time. So when I differentiate b with respect to time, I get b prime of t, or in other words, dB/dt. All right, so this is the second derivative. We're not finished yet because we don't want an answer. We don't want the second derivative expressed in terms of the first derivative. So we want to replace this dB/dt with the expression over here, either one of these. I chose the first one, as you can see. And then going down, I decide to simplify, and I have this final expression for the second derivative of negative 25 plus 4b over 100. All right, and so that gives us the second derivative. The second part of the question says, use this second derivative to explain why the graph of b cannot resemble what we see here. This is very interesting. A lot of questions about this. How can we use the second derivative to check to see if this is the correct graph of b? Right, this is supposed to be the graph of b. We have time versus weight. Now, whenever you're working with a second derivative, you have to just understand that what the second derivative tells us is about concavity. So can we use any information about concavity to sort of debunk this graph? Well, you'll notice that this first part of the curve is concave up, and then at some point we have a graph that's concave down. All right, so let's go ahead and find a point. Let's plug in a point and see if, actually, so if you'll notice, let me just rewrite this down here. D squared b over dt squared is equal to. So the interesting thing is we have a second derivative expressed in terms of b, which is weight. So what we'll do here is choose one of these weights. So let's say, I don't know, something close to 20, let's say 30. Oops. So when I evaluate my second derivative at b equals 30, let's see what we get. We have negative 25 plus 4 times 30 over 100. Now, I really don't care about the actual value. What I care about is positive or negative. So 4 times 30 plus minus 25 would be a positive. Positive over positive is positive. So what does the second derivative being positive tell us about the original function? Well, this implies concave up. And as you can see, we have a concave up part of the graph. So maybe this doesn't help. Let's try another point. Let's try 90. So here I chose b equals 30. Here, next I'm going to choose b equals 90. Now, where b equals 90, we should see, this graph, we're looking at a concave down portion. And so when we plug 90 in for b, we should get a negative number. If this second derivative actually represents the graph that we see here. Well, let's see. Second derivative evaluated at b equals 90. We have negative 25 plus 4 times 90 all over 100. And you'll notice again, you get a positive value. Again, this is implying concave up at b equals 90. And this now debunks the fact that the graph represents, or that this second derivative is modeling the graph that we see, because the graph is concave down when b equals 90. And so you go on to say, therefore, this proves that the graph of b cannot resemble what we see here. Okay, cool. Part C, use separation of variables to find y equals b of t, the particular solution to the differential equation with the initial condition. All right, so the first thing we're going to do, of course, is find the general solution, and then we're going to plug in our initial condition to get the particular. Okay, see. So I'm actually going to go pause this and go back to your questions to see specifically what you asked about this. So 1 second. All right, here we go. So it was just basically people were just unsure of like either where to start or how to get the constant. So anyway, we'll go through the entire problem. So dB dt equals 1/5 times 100 minus b. Okay, so in this situation, I'm actually not going to distribute because it's easier to separate the variables if we do not distribute. So I'm solving for b, which means I need to integrate. But before I integrate, I have to separate this differential equation. So I'm going to rewrite this as dB over 100 minus b is equal to 1/5 dt. And of course, once you separate the differentials, you must then go ahead and integrate. All right, so we have two proper integrals that are equal to one another. Next step is to integrate. For the left side, I'm going to go ahead and use U substitution because a lot of people, or some people were confused about like, why is there a negative on the outside of the antiderivative? So I'm just going to go ahead and kind of show you why it is using U sub. So we have let U equal 100 minus B. du will equal negative dB. Okay, moving on. I'm now going to perform the substitution. So I will have 1 over u, and the dB gets replaced. This, of course, can be written as negative du equals dB. So the dB gets replaced with negative du. So I'll just put that in the numerator. Okay, and of course, that negative can come out front. So I have negative the integral of 1 over u du. And that, of course, is negative ln absolute value of u. Of course, plus some constant. And we want our answer in terms of b, though. So I'm just going to replace u with 100 minus b. All right, so that's the left side. So the left side is negative ln 100 minus b. I'm going to ignore the constant because, again, remember, when we do these differential equations, once I integrate the right side over here, there's going to be another constant, and I'm just going to move all constants to the right side, and they will form yet one constant. So the antiderivative of 1/5 dt is just 1/5 t plus c. So now that's the constant. I had the constant on the left side, I have a constant on the right side, I move them all to the right side, and they form one constant. All right, so we are interested in solving for b. I'm gonna get rid of the negative on this side, so I have ln absolute value of 100 minus b is equal to negative 1/5 t plus c. You might be wondering, well, why plus c? Why not minus c? If you want to do minus c, that's fine. But the point is, it doesn't matter. C represents a constant, whether it's positive or negative. So I can always just say plus c. It's like saying plus negative 2 or plus positive 2, depending on what the actual constant is. All right, so I just like to keep a plus, an addition sign there. Moving forward, I need to get rid of the ln, so I'm going to apply e to both sides, and I will get 100 minus b is equal to e to the negative 1/5 t plus c. If you're wondering where the absolute value goes, check back in my differential equation video. I do go over that. Okay, I just wanted to make sure that I remembered to continue recording. Okay. Hold on, sorry. Okay, there we go. All right, so solving for b. So actually at this point, it might not be a bad idea to go ahead and plug in your initial condition. Although I guess it's not completely necessary. Of course, it's not completely necessary yet, but in general, once you are at this point, you can decide to use your initial condition to solve for your constant, which I think I'm going to do. So the initial condition is that b of 0 equals 20. That means when t is 20, when t is 0, b is 20. So I'll just plug in that information. So I have 100 minus 20 is equal to e to the negative 1/5 times 0 plus c. All right, so I have 80 is equal to e to the c. And this leads us to the fact that c is equal to ln of 80. All right, and I think for now, I'm just going to leave c as ln of 80, and you'll see why in a moment. It actually makes things a little bit kind of simple. All right, back to where we were before. We have 100 minus b is equal to e to the negative 1/5 t plus ln of 80. All right, now here you have to remember how exponents work or exponentials work. So just this right side can be rewritten as e to the negative 1/5 t times e to the ln of 80. All right, so let's keep going. We have 100 minus b still on the left side. That right side, e to the ln of 80 is just 80. So I'm going to bring that out front. So I have 80 times e to the negative 1/5 t. And now let's go ahead and I think we can do this in one step. B equals negative 80 e to the negative 1/5 t plus 100. Okay, and this should be your final answer. Let me see, did they ask for anything else? No, they just asked for the particular solution, and there we go. That's your particular solution. If you want, you can write this as B of t. Okay, I'm gonna go double check to see what questions were asked about the second problem. Okay, so again, there were no questions about part A, but there were questions about part B and C. So I'll go through those. I'll go through them a little bit quickly, a little bit more quickly than I did before. So part B asks us again to find the second derivative and then try to use the second derivative to determine if the tangent line in part A was an underestimate or an overestimate. And a lot of you asked, how do we determine if the tangent line approximation is an underestimate or an overestimate using the second derivative? Remember, the second derivative deals with concavity. And so let's say we have a concave down portion of a graph. If you try to draw a tangent line on a concave down portion of curve, look at this. All of the tangent lines are completely above that curve except for at the points of intersection. So your approximation will be an overestimate. Your tangent line approximation will be an overestimate if your graph is concave down. On the other hand, if your graph is concave up, oops, that was terrible. All right, let's try that again. If your graph was concave up, your tangent lines are all completely under the curve, except of course at the points of intersection. And so any tangent line approximation of a concave up portion of curve will be an underestimate. And so that's basically how you'd answer the question in part B. I don't think too many people asked about how to find the second derivative, so I'm not going to do it. Just follow the steps that I did in the previous problem. They're very, 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 very similar. Part C, again, very similar to the part C in the previous problem, but I'm going to go through it anyway because it is pretty important that we know how to do solve differential equations by separating variables. All right, and so here we go. I'm going to separate the variables. I'm going to put all the W's on one side, all the T's and constants on the other side. So we have dw over w minus 300 is equal to 1/25 of dt. And of course I have to integrate. All right, left side, I'm not going to go through the u sub process. And in this case, since it's positive w minus 300, that there's not going to be a negative on the outside. And you can try u substitution to verify that for yourself. So this is just going to be ln, absolute value of w minus 300. This is going to equal 1/25 t plus c on the right side. All right, apply e to both sides. W minus 300 is equal to e to the 1/25 t plus c. Here is where I like to use my initial condition. W of 0 is equal to 1400. All right, so I have 1400 minus 300 is equal to e to the 1/25th times 0 plus c. So I have 1100, oops, is equal to e to the c, which of course tells us that c is equal to ln of 1100. I'm once again going to keep it as ln of 1100. Hopefully you understand why now. So I have w minus 300 going back to what we had before. W minus 300 is equal to e to the 1/25th t plus c. Of course, that right side can now be, we just solved for c, so I'm going to write that number in there. Of course, that right side can be rewritten as e to the 1/25th t times e to the ln of 1100. Of course, ln of 1100 is just 1100. So we have w minus 300 is equal to 1100 times e to the 1/25th t. And finally, w is equal to 1100 times e to the 1/25t plus 300. Boom, you're done. You can write it as w of t if you want. Not completely necessary. And let me see, did they ask for anything else? They did not. Okay. Just to go back to B real quick. So what I was saying before is if d squared w dt is greater than 0 at 1/4, yeah, at this time, if the second derivative is positive when t is 1/4, then what that means is the graph of w is concave up, and therefore you would have an underestimate. All right, if the second derivative at t equals 1/4 is negative, then you would have a graph that is concave down, and therefore you would have an overestimate. Right? Again, it has to do with the tangent lines being completely below a concave up curve and completely above a concave down curve. All right, ladies and gentlemen, we've already gone pretty long, so that's all for today. Hope this helps, and be well. Bye.